to it.
Oh, hello. I know we just had a lunch, but what can better raise our spirits than learning about sharks? This all is joint work with Mariana Rajkova and Eran Tromer, and I'm Madars. I'm from MIT. So we're here to learn about zero knowledge, obviously, and I'm here to talk about zero knowledge in distributed ledger setting. For example, privacy-preserving cryptocurrencies. And most of those examples, like we know all by heart, they're like almost folklore to us. And we saw them in our previous standardization workshop. And in this setting, it's extremely important that proofs are short and easy to verify, meaning we need SNARKs. So, but which SNARK should you pick when you want to deploy your practical system? Well, the most efficient ones, and the ones that are actually deployed, are based on something called quadratic arithmetic programs. They're maybe a little bit over 100 bytes long, but verification is just milliseconds. It's perfect, except for one detail. They require a common reference string. Or, of course, we renamed, as we do, it's a structured reference string, because it does have a structure. It's a private coin setup. So where does this structured reference string should be coming for? Well, if you have somebody whom you could trust, say, if you're running a large organization, you could trust your IT department to just generate it for you. But we use distributed ledgers because we don't have a single person to trust. So we need to distribute this trust to generate our SRS for our SNARK. And there's a way how to do it, and people have actually done it. Zkers did it. And the way is using multi-party computation ceremony. And the best ceremonies scale to hundreds of participants, and that's roughly how many participants Zkers used. So the probability that it's compromised is like really low. But in 100 years, who would remember that there was all those great participants of our great ceremony? Should we trust their proofs? Like the mythological trust of the SRS string decays over time. So ideally, we would love to avoid setup at all, and we would have a SNARK without private coin setup. And those things do exist. For example, you can use PCP-based SNARKs like libstark. But unfortunately, when you actually go and implement them, they have somewhat large constants, and maybe too large in some settings. Or you could use zero knowledge proofs that are not succinct, not efficiently verifiable ones. And we have many exciting choices here. They are slow to verify asymptotically. For small statements, they'll be just fine, they'll be perfect. But as your statement grows, verification speed decays. So, and in blockchain scenario, fast verification is actually paramount. And I'm going to tell you why. So imagine there are those two Minecraft characters, Alex and Steve. And Alex has a proof, part of his transaction, and he wants to send transaction to Steve. So what happens is this transaction gets propagated through the network. And each node in the network needs to check validity of the proof embedded in this transaction. And of course, if verification is slow, then Steve will see the transaction after a while. So you can say it's like a usability problem, not seeing my transaction when I want it to be seen, like I want it to snap. But it's actually a security problem. Namely, there are other participants in this model, for example, miners. And miners produce blocks, Minecraft blocks. And they need to decide which transactions to include in the block. And therefore, they should also verify all the transactions. But miners don't. And the reason they don't is because each second spent verifying a transaction is second spent mining. So you're losing competitive advantage to other guys who are not verifying. And this is not just like theoretical. People turned off verifying ECDSA signatures in Bitcoin and forked. So, and of course, the fork persisted for multiple blocks because other guys also didn't verify. So verification speed is fast because like if it's slow, then people will just turn it off and like verification be damned. What we have is a system that could help here, and we call it sharks. So sharks are succinct hybrid arguments of knowledge. And those are short proofs that can be verified in two ways. There is prudent verification, which is sort of slow, comparable to bulletproofs, but doesn't require private coin setup. And then there is optimistic verification, which is fast, comparable to, say, Gross16, but which relies on private key setup. And if we had the shark, then what our blockchain scenario could do is everyone could just optimistically verify during the block propagation. And then miners could also just rely on optimistic verification, which is very fast, for a pass-fail check. And then later, during the proof of work, do the prudent verification. And the next miner would do the same, a snap decision here, and then prudently verify during the proof of work. So, but remember, like, those are two verification modes, so how do they interact? Maybe the optimistic verification fails and you learn it during the proof of work. So let's suppose that our generator has actually compromised, sorry, our prover has compromised the trusted setup. It's again from Minecraft. So optimistic verification passes and prudent verification fails. And you can immediately detect it. You have two proofs, one of them passes, one of them fails, detection. And even better, it's a fraud proof for proving that the trusted setup was compromised. Like in a regular trusted setup, you never know. Like maybe it was compromised, but it wasn't. And here, like seeing a single proof for which the two verification predicates don't match is a fraud proof for the setup. So what you would do, you would automatically propagate this fraud proof, and you would revoke the SRS. But you can also recover from this. You recover soundness by just switching back to prudent verification. And you recover speed by regenerating the setup string and refreshing all the optimistic proofs. So you can do optimistic verification again. And actually, it's a requirement for our primitive that anyone can refresh without knowing the original witness in the original NIZK proof, in original prudent proofs, I'm sorry. So you could even imagine a system where you have multiple optimistic setups, and like, I like this one, so I'm going to use it for some people, and some people like this one, so they're going to use that one. So I think sharks are great, and I want to show you how to build them. So let's try a generic construction of a shark. It like looks like a NIZK and SNARK somehow tied together, so maybe it's just a parallel composition of NIZK and SNARK. So what we are going to do is to construct prudent proofs. We are going to pick a language and construct a NIZK for it. So our prover takes an input and witness, produces proofs that instance is really in the language, which the verifier can later verify. And we will call this proof a prudent proof for our shark. And then we can construct the SNARK for the same language. And here it is. But this composition has the property that optimistic proofs require knowledge of a witness. But in a shark, everyone could regenerate an optimistic proof given a previous prudent proof. So this parallel composition is not a shark. So shark is not just concatenation of a NIZK and SNARK. Let me show you how to actually achieve sharks. We start, as previously, by constructing a NIZK proof system, which will be our prudent proof. And then constructing a SNARK for the statement NIZK verifier accepted, meaning that SNARK prover will take as its input an instance plus a NIZK proof and produce a proof of the statement that had I run this NIZK verifier, it would have said OK. And of course, SNARK verifier can verify it. And this we would call the optimistic proof. And this will, in fact, be a shark. It has properties that we alluded to earlier. So here's a generic way how you would get a shark. I don't want a generic way. I actually want to implement it. So what would happen if I just took state-of-the-art components? I took state-of-the-art NIZK, namely bulletproofs, and state-of-the-art SNARK, namely Gross16. Well, I would start by picking a circuit that I care about. And then my NIZK verifier would take roughly lambda times circuit size group operations to do the NIZK verification. But in its belly, the SNARK prover needs to eat the NIZK verifier. So what you get is that the SNARK prover runs in time lambda squared group operations So I started by something that's OC size, and then I suddenly arrived at this lambda squared factor. So it is still a shark, but it's kind of a chubby shark. So I like fit sharks. I want my shark to be fast. So I'm going to show you how to get a fast shark. Namely, our technical contribution builds as follows: that we first design a NIZK for R1CS. And if you went to Cassie's talk, you know that R1CS is essentially arithmetic circuits with bilinear gates. And our NIZK internally will be using a new compilation technique for linear PCPs. And we'll be able to get public coin NIZKs from linear PCPs, which will serve as our prudent mode proofs. And then we also present an optimized variant of bulletproof's inner product argument that our NIZK will also use. And I didn't need to go through the step of linear PCPs and optimizing bulletproofs, but I did because my NIZK verifier now is going to have a very algebraic heart. The verification is going to have very nice mathematical structure. And what I'm going to do next is I'm going to construct a special purpose SNARK that only cares about verifying this problem that we introduced that we call encoded polynomial delegation. Cannot verify arbitrary circuits, can only deal with this. But this is how we'll get a shark. Our shark will be this NIZK plus our special purpose SNARK. I want to get to the algebraic heart of my NIZK verifier, so I need to open up a NIZK and show you how it looks like. So let me do that. Let me recall a very productive paradigm of Bitansky et al. Called linear PCPs. And they generalize on abstract away quadratic arithmetic programs. And they operate in two steps. You first design a proof system sound against linear provers. I'm going to tell you what it means. And then you force, using some sort of cryptographic encoding, your prover to be linear. So linear PCP prover, just like a regular prover, would take an instance and a witness and produce a proof string. Linear PCP also has, fascinating, there is some hand. A query sampler, which takes some randomness and outputs queries. And also outputs a verification state for decision algorithm later. And those queries are answered as inner products with the proof strings. This is like where the linearity property comes in. And then decision predicate can take query answers and either accept or reject. But it's very important to enforce that linear PCP queries are answered as inner products. Otherwise, this becomes meaningless. So we'll use crypto for that. And of course, in this model, you can define natural notions of completeness, soundness, zero knowledge, but I won't do it here. So let me show you how we could compile this in a public coin NIZK. I'm going to do it using interactive proof systems that I'm going to later squash down using Fiat-Shamir transform. And our interactive prover will first observe that linear PCP prover doesn't need to know queries a priori. So what it can do is run the linear PCP prover and obtain a proof string, then commit to this proof string, say using a Peterson commitment, and send it to the verifier. The verifier will now pick coins for the linear PCP query generation algorithm and send them back to the prover. And prover can now run the linear PCP query generation algorithm, obtain the queries. And this compilation technique that we have here is different from what, say, BCIOP did previously, where they cared a lot about hiding the queries. So you use linear-only encoding for queries. And as a result, you get a private coin setup for a SNARK. And our goal here is getting public coin setup for a NIZK. So we take a different route. So our verifier can now obtain answers to each of those queries from the prover. Prover will helpfully compute them. And then verifier can run its decision procedures, namely first compute the state and then plug it in together with answers and decision predicate, and check if this accepts. So those steps are like kind of translating what happened here in interactive cryptographic protocol. And the main meat of this is going to be actually proving that queries were answered consistently as a linear function of the proof string that was previously committed to. All of the steps here are easy. The step 5 is actually complex. So let's look in how we can prove that queries are answered as inner products. So here what we are going to do is verifier knows randomness for the query generation algorithm, knows the answers, and knows a committed proof string. He wants to check that for every query, its answer was committed as inner product. And what we are going to use is inner product arguments, the same inner product arguments that are used, say, in bulletproofs. And input for an inner product argument at a very high level is 2 vector Peterson commitments and an alleged inner product value. And what inner product argument does, it proves that you can decommit them in a way that satisfies this inner product relationship. So it gives us a compilation strategy here. Because our verifier can compute commitments to queries and then invoke inner product argument with a previously committed proof string, commitment to the query, and alleged answers he got from the prover. And this is how you get NIZK from linear PCPs. In our setting, this would be how you get SNARK prudent proofs. But this is not yet a SNARK, because computing each of those queries is going to take you linear time. So we're going to work hard to make the verification efficient. So let's look what verifier does internally. So the heart of our NIZK verifier is this. It first checks that linear PCP decision predicate accepts. It's kind of cheap. Then there is costly something, which is computing those commitments to each of the queries. And the costly part number 2 is running the inner product arguments verifier. Of course, there are other things like checking Fiat-Schmidt transform and whatnot. I'm just highlighting them here. I don't want to do, NIZK verify doesn't want to do the costly part. So I'm going to make SNARK prover do them. And we do that by introducing a new building block called encoded polynomial delegation. Some of you have heard before about verifiable polynomial delegation. It unfortunately doesn't suffice in our setting, but we get encoded polynomial delegation. We make friends along the way. So I will focus on just the first one in interest of time. Let's see how we can compute commitments to each linear PCP query efficiently. So remember that our goal is computing commitment to a query vector. And this query vector is output of a query generator algorithm. And there are many linear PCPs, but the most efficient ones are based on quadratic arithmetic programs. And those have extremely nice algebraic structure inside, meaning the randomness of the query generation algorithm is just one field element. And then the queries themselves are evaluations of low-degree polynomials at this evaluation point, the randomness. So if I write each of my low-degree polynomials explicitly in the following form, and I can see that I can rewrite my query vector as follows. It's first a vector of all the constant terms plus evaluation point times vector of all the linear terms plus and so on. So what I have done is just like rewritten this polynomial vector of polynomials in a slightly different form. But this form is going to be productive for me because if my goal is to compute a commitment to this queue, then because commitments are linearly homomorphic, they kind of go through my equation. So I get commitment to query vector is commitment to all the constant coefficients plus tau times commitment to all the linear coefficients plus and so on, commitment to all the highest degree coefficients. So the verifier's goal is to efficiently compute the expression on the right-hand side. Here's how we do it. So we're going to outsource it to the SNARK prover. And we first notice that all the polynomials are completely fixed by choice of the circuit that you made, by choice of the language. So all those commitments take a fixed value, and the only thing verifier wants is, given a tau, evaluate this expression. So we abstract it away, and we create the following problems that for fixed parameters, u0 through ud, where each u is going to be commitment of some polynomial coefficients. Our goal is, given an input point tau, efficiently compute this expression. And this looks like polynomial delegation, where the coefficients for the polynomials are group elements. So we called it encoded polynomial delegation. And our result here is a new building block. We achieve a SNARK for encoded polynomial delegation in pairing groups. And moreover, we are able to generalize this to a multilinear variant, which is useful for verifying inner product arguments. And this will be the key ingredient of our SHARK optimistic proof. Actually, the main ingredient in our SHARK optimistic proof. Let me take a step back and look what we just did. So putting things together, this is the picture that we had before for the generic construction. And the way that we instantiated this picture, the SNARK prover only needs to care about encoded polynomial delegations, because our NIZK verifier had this very nice algebraic structure. So we are able to have a SNARK prover that's reasonably sized, and verification is also going to be just a couple batchable pairing product equations for us. So finally, this is where we are. If you remember the slide from before, that had you just used state-of-the-art NIZK plus state-of-the-art SNARK, you derive a lambda squared slowdown for your SNARK prover. And in here, we have a compilation to a NIZK that gets you lambda slowdown for the NIZK verifier, but only lambda slowdown for the SNARK prover. Also, our proof sizes and verification time are competitive with state-of-the-art NIZKs and SNARKs. For example, our SNARK proof is going to be 5 pairing equations and 6 G1 elements, where 3 of them are proof for encoded polynomial delegation, and 3 of them are just instants that you want to be delegated. So to sum up, we introduce a new primitive where private coin setup is only needed for performance, and public coin setup suffices for soundness and zero knowledge. In our setting, compromised setup can be easily detected and quickly replaced. And speed, we estimate, is going to be competitive with best current SNARKs and NIZKs. And of course, we made friends along the way. Thank you very much.
All right, we have time for a few questions. If anyone wants, right there. I'll get the mic to you.
I'm Ivan Visconti from University of Salerno. Can you go back to the slide putting things together? It was like 3 slides ago, I think.
OK.
Thank you. OK, if I understand correctly, here the prover of the SNARK is proving a statement about VNIZK, right? Is it that correct?
Yeah.
But VNIZK, if I'm not wrong, was using Fiat-Shamir transform inside, right?
VNIZK, yes, but the SNARK prover, but those are the cheap parts of the VNIZK verification.
Yeah.
So yeah.
OK, let me go straight to the point of my question. So if that NIZK is the one on top, VNIZK, is secure in the random oracle model or not?
It is.
Yeah, so if it's secure in the random oracle model, then proving a statement about that VNIZK, it's a bit complicated, I think, because it's basically you don't have the description of the hash function that the verifier is using, the VNIZK is using. You cannot use it because it's a random oracle.
So
how do you defeat this problem.
Okay.
Yeah. Thank you.
So if I understand correctly, you're asking, what if I wanted to instantiate v-NIZK in a random oracle model and then actually get the access to this random oracle as, say, a circuit and then operate on it in a SNARK? So our SNARK is, for example, it's not required to be zero knowledge. It's not required to be proof of knowledge. It's only for speeding up things. So the hash function evaluations in the SNARK verifier will be done by direct queries to the random oracle. And the only thing the SNARK verifier does that's substantially new is verifying this polynomial delegation.
Okay, we are actually out of time, I'm afraid. So if you have any further questions for Madars, he'll take it offline.